Hi, now we'll continue studying single DTR. So let's first review what we studied in the previous class. So dx is a treatment regime, and uh, from so using d we can derive, right? We can derive the potential outcome. So originally, potential outcome has been defined on in terms of A, right? On the A, but because of the room, because of the mapping, we can derive the potential outcome for on the D, right? And then expectation of the potential outcome is a value, and our goal was to estimate the value using the data, and this one is this guy, right? But we already discussed. So section two, chapter two is about estimating this guy, right? And so we use basically the same idea to apply the technique, but only thing is that we have to derive the corresponding quantity. So so to estimate the value, we can use outcome regression model approach or IPW approach or augmented IPW approach. Okay. So the key goal is we wish to find an optimal treatment regime such that it is optimal. It maximizes, right? The maximizes the is expected outcome. So this is the basically the expected outcome, but it's expected potential outcome. And so we want to maximize the expected potential outcome. Okay, and uh, here's two. So to discuss how to do that, we want to use a simple example. Okay, so now let's consider 0 and 1 situation. So a binary action situation. Then the value function, our value is basically uh, dx equal to 1, right? Or dx equal to 0. And then the corresponding conditional expectation. So this guy is basically is what? Let me write it. So let's be what A, where A is either 1 or 0. So we can actually write it as a 1 and then dx equal to 1. Uh, dx equal to 1 plus, let's do, sorry. So write it this way. Plus y star 0 dx equal to 0, right? That is just the given x, because we have a given x, right? So given x, this is just the same thing. And then given x, y star 1 given x times I dx equal to 1 plus 0 I dx equal to 0. So qxd, qxa is expected value of y two properties. One is this, but you can also write it as a so so the first expression is in terms of the observed data, while a second expression is the in terms of the potential outcome. But they are equal. So that's why we get this equality, right? So so then if this function is known, right? If this function is known, then turns out that is how to maximize this. So the solution to maximizing the inside. So how to maximize this is actually the solution is this. So to understand why, let's use this toy example. So this is a really simple example, but hopefully it'll actually give you a good idea about what's going on. So this is really easy problem, right? You have qx0, right? 2, and then this is linear with qx1. And what you are interested in is maximize. So you want to compute the. So what do you mean by this? So what basically dx is either 0 or 1, right? So basically that means uh we just choose one of the two. Either for each point, for each x point, right? For this point, which one you want to choose, which line you want to choose. Uh, the goal is to find the maximum, right? So for this particular x, the maximum is this, the first line, right? Of course. So basically we want to choose this. But what about this point? Well, the maximum changes, right? We want to choose this point. So basically this is the choice. So then this is 1. So basically the dx is equal to 1 or 0 if x equal to greater than 1 or x is greater than 0. So that basically using this graph. So basically it means we at each point we basically choose the option corresponding. So we want to choose the option that has the largest Q value, right? So that's basically this idea. So this one has a large, right? So we have choose. Okay. So basically that is the optimal regime. So optimal regime is nothing but this is Q, QXA. So so once you know this Q function, you just choose the whatever the option that has the largest value of Q function. That is the optimal regime. So that is basically the main result. And then once you choose this one, then you will get the you will guarantee the optimal result. So so okay. So to show this, right? This is what we want to show. So we want to show this. Those two, but by the way, this one is an expectation of the y star potential outcome of the, I mean, on the D, and then this guy is a y star of general D, right? So this is the marginal expectation, but But to satisfy this marginal, relationship, we only have to satisfy the conditional inequality. So this will lead to, if you take the expectation of this, right? Then we'll get this result. So now let's take a look at this one. And this is actually, by definition, a maximum over the Q function, right? So then your this is 1. So this is actually 1. Any event chooses any decision rule choose one of the options. And then this, because this is maximum, this maximum will, because this is max, if you remove maximum, then you will get inequality here. So then you will get, so then you can, this guy, if you make the, remove the maximum and then it can go inside, you get this one, which is this one. So that basically proves the this result. And now, so using this result, right? So this proposition basically says that as long as you know Q function, you are in a position to find the optimal region, right? Optimal dynamic region. And so that is basically the idea. So we wish to estimate the optimal region from the data, and the most straightforward approach is the regression-based approach, which is sometimes called Q-learning. Seven-parametric approach using contrast function is A-learning. Value search estimation method is another one. Okay, we'll study one by one. So the Q-learning, we wish to use the first proposition, right? So we only have to utilize this result, right? This one will imply this one. So that we want to use basically Q function directly, because this is the optimal decision rule, uses the option that has the largest value of Q among the options that we have. Okay, so basically, posit a parametric model on Q, right, on the conditional expectation, and obtain beta hat, and then plug in, and then use that to find the optimal treatment regime. So the subscript Q denotes that we are using the Q function, which is the Q-learning regression estimation. That's it. The only thing may deserve discussion is that even though this Q OPT X is actually function of beta, right? Because you use beta hat. So this guy is function of beta, but this is non-smooth function. So you don't have the you cannot really apply a linearization technique directly for inference. Now let's move on to A-learning. So obviously this Q-learning requires that this model is correct, right? The model for A equal to 1, model for A equal to 0, and so maybe it's a little bit too strong. A-learning, we want to kind of use the less assumption. So here's the motivation. So remember, for the 0, 1 situation, this is the optimal regime, right? And if you somehow define the contrast function, so we have a name, which means that it must be important. So the contrast function, if you define this way, the optimal regime here can be written as a function of contrast function. Okay. So notice that we don't really need Q1 and Q0 to be known. All you have to know is the difference between Q1 and Q2. That's all we want to know. So that may be a less assumption, require less assumption. So That is the main idea. Okay. So the idea is we can use A. So you write, you use contrast. So this is a contrast function, right? Contrast function. And A, if A equal to 0, so if A is 0, then what? Then this is 0, right? Second term is 0. That means Q V1, I mean new X is Q0, QX0. So that is kind of baseline outcome model expectation. And usually Q equal 1, right? I mean, if A equal to 1, then this is basically the what we are interested in, because for in terms of the optimal regime, finding the optimal regime. So let's use a semi-parametric model of this form, where nu is fully non-parametric and Cx is a parametric with the unknown parameter psi. And then the point is that this nu, right, the first non-parametric component is relatively unimportant, as we are mainly interested in finding the optimal regime, because we are mainly interested in estimating Cx, contrast function. So, okay. So then that means we are not really worried about this is exact estimation of nu, but we really want to very careful on estimating the contrast function carefully. So that means we want to, if the model is correct, we have only to estimate psi carefully using the IID observations of the data. So that is an interesting problem, and that was first considered by James Robbins when he was not really famous at the time. But anyway, he already figured out at the time. So so he actually viewed this problem in the context of the epidemiology context, and he viewed it as a structural mean model problem. So the structural mean model is that we basically have a so this is a baseline still, and then this is kind of a basically the A times, right? A times C is this gamma. But in this literature, this is just a gamma function, and the gamma function should be 0 at the baseline. So it's a 0 at baseline, but it's could be non-zero uh could be non-zero at for other A's. Okay, so that is often called the blip function. And this G is a link function. So we can, if Y is binary, right? Then we don't want to make we may want to use a logit link function to make it more continuous. So James Robbins proposed the so-called G estimation method to estimate a parameter psi 0 in the blip function without requiring correct estimation. So the uh so this is actually class. So any RAL estimator of a psi in 3, right? In this model. So we are now talking about this model, this semi-parametric model. Can be expressed as a solution to the following estimating equation. So A minus pi x, and then y minus ax, and we're gonna almost always use this choice. But the point is that if you use this one, this nu is non-parametric, right? So it's not really good. So what you can think of is you can use some kind of a parametric sum model, something like that. But anyway, this covers a very general class, uh, but but so uh, so and then the choice of lambda. So if you so this is actually parametric, right? Because this is a parametric. So this so that means lambda is also parametric. So this is parametric, but pi could be non-parametric, right? So we allow pi x to be non-parametric, nu x to be non-parametric, but C is parametric. So so that's why it is semi-parametric method. Okay, so let's take a look at this equation. So how can we understand? So the conditional is so let's take a look at the expectation, right? We want to compute the conditional expectation. If you take the conditional expectation, given x and a, the only thing random is a is y. So you can actually obtain this one. Okay, and then this guy is equal to nu x, right? Because of the model 3. So you end up getting this one. Okay. So if the propensity score pi is correctly specified, then second term, this term is 0, right? If we have a model for nu x, which is the baseline Q function, and use that to be the minus of the zeta x, then the second term, the last term is 0 under the under the assumption that the working model for Qx is correct. So that gives a very interesting doubly robust estimation argument. But basically we can have two propensity models. One is this one, the other one is this one. So propensity score model is the model for A given X. Outcome regression model is Y given X and A equal to 0, right? So if one of the two model is correct, then we are good. So because this is a parametric sum model, we can use estimate easily from the data and plug in, right? Plug in and solve this for psi. Again, if the propensity model score model is correct, then this term is 0, right? If the outcome regression model is correct, outcome regression model for y given x and baseline is 0, correct? So this model is correct, then this term is 0. So that means this term, second term is 0. So either this term or so that is 0, but if 1 is true, 0 if 2 is true. Okay. Once psi hat is obtained, the rule, the optimal, characterize the optimal treatment regime can be estimated by this. So that's very, very useful result, right? And now that is famous G computation, G estimation method of Robbins. And then later, Susan Murphy, she's also very famous. Uh, reframe the problem in terms of the advantage function. So that is her idea. So what is the advantage function? So basically you can think of this way. So this is the optimal, right? Remember, the optimal decision rule is this one. And this is what? This is not optimal. This is just the given, right? Realized. So this is basically the difference between what you would get, right, as the best option versus to the realized option. And then this is basically price tag, the difference of the price. So for example, for binary options, if A is 0 and 1, this guy can be -1, right? Because you have a 1, 0, 0, 0, 1, 1, 0, 1, 1, right? So D, D and A. So then subtract. So difference could be, the difference could be 0, -1, 1, 0. So we are talking about this. So so this case, these two cases, no problem, right? So our optimal choice happen to be the same as what you have currently have. So that's not really big deal. But 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 these two, right? These two actually you basically compare with the best option minus the current option. Okay. So that is actually the advantage in the expected outcome if the optimal option were given relative to that actually received. So that is advantage for opponent. For me, it's a regret, right? So it could it's a regret incurred by not using the optimal option. So Murphy developed this A-learning method based on the direct modeling of the advantage function and rather than contrast function. So that is very interesting idea, and that could be so she is now at that time she was at University of Michigan, but later she scouted, she become very famous, get some got the award, and uh, she's now in Harvard and uh, doing some fancy stuff in reinforcement machine learning, things like that. Anyway, so so that is the basically about the QA learning. Okay, and now let's take a look at the what would be the maximum, right? The optimal decision rule more carefully. So it has a name. So if we choose, right, if we choose the optimal decision, optimal rule, then the expected conditional expectation outcome as a function of x is the best you can, right? Is best you can achieve. That is sometimes called the value function. Okay, so value function is a conditional expected outcome obtained using the option selected by the optimal rule, right? So then, of course, the expected value of the value function is a value of the optimal rule, which is expectation of the best Q at each x point. We can choose the best option and then take the average, take the condition, take the expectation. So so that means the on the expression 3. So remember, this guy is nu x plus a times cx, right? And the best option, so the best option is the optimal one. Optimal one is I cx is greater than 1. Sorry, greater than 0, right? So that's this one. So that if you plug in, that's the best you can do. That's the best maximum. So the maximum is just the choosing using this rule, optimal rule, this one, and then that is the uh, um, value. Another expression for the value function. So this is the kind of baseline, right? And then this is basically a contrast times optimal contrast times optimal rule, right? Optimal. So this is rest times the optimal. So why this is so that actually so that is for the value function, and now so this is the value function, right? And now we have another interpretation. So value function can be expressed in terms of the advantage function. So that is an interesting interpretation. So that is so A is what? A is current my observation, right? So this is what I have, my my status. This is what? Advantage. Advantage means the what I could get, right? If I had chosen the best option, best decision, then this is what my advantage. Then this is what? This is the basically the value function, which is the best you can do, right? So conditional expectation obtained using the option select by. So this is the basically best. This is you can say that current or present. So real, right? Reality. I can say reality. This is my reality. This is my ideal, right? My ideal me, and this is the advantage. Well, we need to show that, but a nice thing about this one is that we can actually so I I can use my current data and and directly obtain. So this is advantage, right? This is advantage, and then this is my current observation to estimate the optimal I mean the value estimated value at the current at the best optimal decision. Uh, okay, so that's very interesting concept. The statistical inference is, however, is challenging because they are non-differentiable functions, right? So the whole idea is that the optimal x is I C x p hat is so this function, right? This function is non-smooth, non non-differentiable, right? It's not just that it's actually non-smooth. Okay, so now you are in a position to show equation 7. So how to prove 7? Uh, okay, so that is what you want to show. Okay, so let's prove that. This is what we want to compute. And we first the conditional on x and a, and then uh, x and a, the only thing random is y, so we get this one. Okay, and then what is y, x, and a is basically qa, qxa, right? So qxa is nu x plus a times cx. So that's basically this one. And then once you do that, you actually have some nice cancellation. So you end up getting this one, which is this one because of the result in here, 6. So you have a 3. So you use 3 and 6. Okay, so that basically take care of the Q learning and A learning. Now we have one more thing to study, which is called value search estimation. So this is uh, proposed by Chiatis group. I mean the Davidian NCSU, and the textbook is written by the NCSU group. So that's probably why they included this topic. Uh, uh, well, that's interesting actually. So the The idea here is the motivation. So now let's consider this. Suppose my contrast function is this one. So the idea is that the Q-learning or A-learning uses a model, essentially uses a model for Y, right? But the model derive, right? At the end of the day, the model, suppose your model Q x1 minus Q x0. So each model is linear in X, right? Linear in X, linear in X. Then the difference is linear in X. So that means the region, right? This optimal rule is still a indicator function of the linear on X. So something like this. So the idea is, okay, we could use Q learning or A learning to estimate the parameter. But here's another way. Another way is let's just treat this parameter unknown, right? So let's just write directly make a model for the decision as a linear function of X. I mean, indicator, of course. So some function of X. And sometimes we have a very good idea of what the rule is, but we just don't know the parameter in the rule. In that case, we have only to use the value function, use the estimate of the value function, and find the optimize it. Because by definition, the optimal decision is what? Optimal decision is the one that maximizes the value function, value, right? So this is the estimated value. So that kind of intuitively makes sense. So we already studied how to estimate this, right? And so this is basically the idea. So if you can somehow write it as a function of eta, and then you can, if you can compute the estimator, then you can plug in to obtain the optimal treatment regime. So here's basically some toy example. I mean, conceptual example. So now we have a parametric model for the optimal treatment regime with a unknown parameter eta. Okay. And then we already, I mean, the particular form of the new head, I mean, this V hat Q is actually a topic that we studied before. Let me see. Uh, right? I mean, if you look at the um, this one, I guess. If you look at this Q-learning, this one. So optimal regression estimator of the value. So basically we have a outcome model, and then we have a decision rule. And in this case, this decision rule is known. Dx is known. But now the tricky part is that the decision rule is known up to eta. So that is known up to eta. And then we basically use this one as a function of eta and then optimize. Same way, if you know the D, then we can derive the IPW estimator. This should be V. Yeah, a lot of notation. But the concept is essentially the same, right? Because in chapter, so previous week, I mean previous class, value function of D had, we studied all about this when dx is known. Now the only thing is that this is known up to parameter eta. So then you can use the same estimator, but now you express it in terms of eta and optimize. So this is a Q estimator, regression estimator. This is IPW estimator, and also we can also develop the augmented IPTable estimator, right? Using the dx eta. So the conceptually, the value search estimation approach is interesting, but the computation for optimization is really difficult. And so that is a limitation. But they had another idea on how to do that. So they have some idea for using the classification method, which will be topic of the next class. So that's all. And here's the reference. Thank you for your attention.